NMR is one of the most powerful tools to determining the structure of the organic compound. But what if I told you it can also be used to determine the yield of your reaction without purification? Yes, there are two practical methods by which you can determine the yield of your reaction using the NMR technique. The first, in which internal standard is added in the beginning of the reaction, and the second, in which internal standard is added after the workup. In this video, we are going to see step-by-step procedure for method 1. By the end of this video, you will clearly understand how to calculate the product moles, how to calculate the yield, and even the conversion directly from the NMR. Hello friends, welcome back to my channel Dr. Vijay SSOC. So let's start this video. Method 1, internal standard during reaction. This method is ideal for accurately determining both conversion and yield by incorporating a known amount of internal standard directly into the reaction mixture. This is best method during the optimization of the reaction because you don't need to waste your time in the purification. You will directly calculate the yield and conversion from the NMR. Now we are going to see each and every step, how to do it practically, and then how to do the calculation for this. First step, set up your reaction as usual. Note down the millimoles of the limiting reagents. For example, I am doing amidation of the benzoic acid. So I have taken 1 gram of the benzoic acid, which is equal to 8.188 millimole. This is the limiting reagents, and this amine I have taken in the excess amount. Okay, so after this, just add internal standard in the reaction mixture. Okay, so first you take the benzoic acid, amine, everything, then add internal standard into the reaction mixture. How much? You can add 30 to 50 mole percent. You can add more than that also, up to 1 equivalent is fine. Adding less than 20 or 30 mole percent is not recommended because you can have low intensity in the NMRs. Because of the low intensity, you will have error in the integrations. Therefore, it is better to take in between 30 to 50 mole percent or up to 1 equivalent. Okay, now I have taken 1,3,5-trimethoxybenzene as an internal standard in this reaction, which is 50 mole percent and equal to 688 milligram. Why I have taken this internal standard? Because this is soluble in the organic solvent and it is non-volatile, and it will show 9 protons from this methoxy and 3 protons from the benzene. If the benzene protons get overlap, then I will have at least these 9 methoxy protons, right? And the signal intensity will be higher as well because of the 9 hydrogens. So therefore I like to have this kind of internal standard. Now what is the criteria to choose the internal standard? So the internal standard should be chemically inert. It should be stable under the reaction condition. It should not decompose or it should not get react in the reaction condition. It should be non-overlapping with the peaks. This is very important. You must know that your internal standard is not going to overlap with the peak of the starting materials or product. Otherwise, you will have wrong integration value and you will have wrong NMR yield. You must know the known purity of your internal standard. It is better to have your internal standard above 95% pure. It should be non-volatile as well, because if it is volatile, then during the evaporation under the rotavapor, it will evaporate and then concentration will change, the amount will change. So it is important to have non-volatile. It should be soluble in your organic solvent. If it is not soluble or partially soluble, then you will have a non-homogeneous mixture and it will give you the error. So therefore it is important to have proper soluble internal standard. So I prefer to use this type of internal standard. In case this is diurine, which has 4 methyl groups, so it will give 12 hydrogens, right? And 2 protons from the benzene ring. This will give 9 methyl hydrogen. This will also give the 9 methyl hydrogens. So let's say if aromatic protons get overlap, then at least you will have methyl protons to do integration, right? So therefore I like this kind of internal standards which can have 2 types of the protons. Okay, now let's move further. The step 3, run the reaction according to the procedure. So you can do stirring at room temperature, reheating as described in the procedure. Your internal standard stay constant throughout. It is not going to decompose because you have already chosen such internal standard, right? Now what you have to do, after finishing your reaction, take aliquot of the reaction from the reaction mixture. If you need, you can quench by adding methanol or isopropanol. Please note down that volume of the aliquot is not important. We are not going to use the volume in the equation, so therefore we don't need volume of aliquot. I will show you why we don't need volume of aliquot during the calculation. Now step 5, sample preparation. Remove the solvent. Okay, so you took the Aliquot, for example, you have DCM or methanol. So remove this solvent till the dryness. Now check how much amount you have. If it is less than 3 milligram, so it is better to take some more amount of the Aliquot, because the residue amount should be more than 4 milligram. Then only you will have nice NMR. If you are taking less residue, then your NMR integration will be lower and noise will be higher. Then you will have wrong integration. So it is better to have good amount of the residue. After that, dissolve the residue in the deuterated solvent, for example CdCl3, or you can take any other solvent, but make sure it should be soluble properly. If it is not soluble properly, then it can give you the error, because if product is not soluble, then you will have partially soluble product in the NMR tube. Or if it is starting material is not soluble, then also you will have problem in determining the conversion. So make sure the deuterated solvent which you are choosing must solubilize the sample properly. Okay, now what we have to do, run the NMR. Okay, so for running the NMR, it is better to choose qNMR. Q stand for quantitative. So when you go to take the NMR, you will see this kind of the experiments. So look for this experiment 1H qNMR mode experiment. Why it is important? Because qNMR has long relaxation delay, so you will have accurate integration. If you are going to do the normal 1H NMR, which has short relaxation delay, which is faster, then you will have error in the integration. So please consider in that case 5 to 10% of error. Okay, for example, if you are getting an NMR yield 50%, then it is actually 40% or 45%. Okay, but if you are using qNMR technique, then your yield will be more accurate. Now let's say this is your NMR. Let's move to the step number 6. Peak selection. We have to carefully select well-resolved non-overlapping peaks for the reactant if you want to know the conversion, for product if you want to know the NMR yield, and internal standard for accurate measurement. Okay, please remember, we don't need all the signals of the product non-overlapping. If others are overlapping, only one should be non-overlapping. That's enough. Similar for the reactant internal standard. One non-overlapping peaks is enough. Now if you see in our NMR, let's assign those. So this is the internal standard peak, because it is coming from the benzene part. This is coming from the methoxy. These are the signals from the product, because it is from the ethyl part. This is CH2, this is methyl, and this is the unreacted starting material signal from the carboxylic group, right? So we have assigned all the signals carefully. Now let's move to the calculation part. First, we will calculate the product moles by using this equation, where N is equal to the number of moles of the product. This I stands for the integration of the product, and capital N of the product means number of protons corresponding to the chosen peak of the product. Okay, IS stand for the internal standard, so integration of the internal standard, and capital N means number of protons correspond to the chosen peak of the internal standard. Now before moving to the calculation, I would like to explain you how we got this equation. Integration in NMR is not equal to the number of protons, because it depends on the experimental condition and scaling factors. Instead, it is better to say that it is directly proportional to the number of protons, which is why only ratio of integrations are meaningful. Okay, so integration is directly proportional to the number of protons. Okay, so how we can write integration of the product is directly proportional to the number of protons of the product for the chosen peak. We can also write this equation in this form, where we introduce the concentration part. So C is equal to the number of moles of the product divided by the volume. Let's say this is equation 1. Similarly, we can write the equation for the internal standard. So internal standard directly proportional to the concentration of the internal standard multiplied by the number of protons of the internal standard. Now you have to divide equation 1 and equation 2 to get the equation 3. Okay, so when you divide equation 1 by equation 2, the V, which is sample volume, which is same for both, because you are taking in the NMR tube. So in NMR tube you have internal standard, you have sample, so both are in the same volume, so V will cancel out, right? And after cancelling out this V, so we don't need to know what is the volume we are taking for the NMR samples. And in the beginning, when we were taking the Aliquot, that time also we don't need to know the volume, because the most important thing is ratio of the integration of the product and integration of the internal standard will remains the same. Doesn't matter you took the 1 ml or 0.5 ml, integration ratio will remains the same. That's why volume doesn't matter. Okay, now we understood very clearly that what is the source of this formula. Okay, let's move further. Now we have to calculate the NMR yield. So, and for NMR yield, the formula will be moles of the product divided by the initial moles of the limiting reagents, and our limiting reagent is benzoic acid, right? You can also use another formula, which is observed NMR yield divided by the theoretical yield. For observed NMR yield, you need amount in the gram or milligram, right? So let's say this is the integration value 1 for internal standard. I am starting integration for directly from this, so of course it will be 1, right? And then integration for the product I observe 0.34. Okay, now I am going to apply this equation which we saw in the previous slide. So after applying this equation, you can see that 0.34 is the integration of the product divided by 4. This P is corresponding to 4 protons from this CH2 CH2, right? CH2 CH2 is 4 protons, and this peak is corresponding to the 9 protons. That's therefore 1 divided by 9. And this one, do you remember what is this? This is number of moles of the internal standard, which is 4.094. We took this much internal standard, right? Okay, now after solving this equation, we observe N product means number of moles of the product is equal to 3.1319 millimole. Now we can calculate the NMR yield by using this equation. So this initial moles of the limiting reagent is 8.188. So after solving this equation, we have 38% yield, NMR yield. If you want to use this equation, then this number you have to multiply by the molecular weight of the product, which is 177. So multiply it, you will have milligram. Then you can determine the theoretical yield and then use this equation. Okay, but this using this equation is much faster because you are having the result in millimoles. Okay, now we have NMR yield. Now we are going to see how to calculate the conversion. For calculating the conversion, the formula is very simple. Look at here, NRS. R stand for number of moles of residual starting materials or unreacted starting materials, or NIs stand for the number of moles of the internal standard, which we have seen previously. Okay, after solving this equation, you will have a number of moles of the unreacted starting material. So let's solve this equation. First we are going to do integration of this unreacted starting material, because this part is overlapped, so we don't know which is coming from the benzoic acid. Okay, so I'm not going to take integration of this one. I will take integration of this carboxylic group. Okay, so the integration of the starting material is 0.1. So now we are going to use this equation and let's see what is the result. So after using this equation, we are getting 3.648 millimole of the unreacted starting material. So 0.1, this is the integration, and this corresponds to 1 proton, right? And we have already integrated this one, which is which is equal to 1 and correspond to the 9 protons, right? So after solving this equation, we are getting this millimole. Now we are going to apply this equation. Okay, so after solving the bracket part, we are getting the 45%, and 45 minus 100, so we have 55% conversion. So the yield, NMR yield was 38% and conversion is 55%. It means that some amount of the starting material is converted into something else, right? Everything is not converted into the product. Some may be decomposed or converted into something else, right? So that's why the results is the conversion is 55%, but the NMR yield is 38%. Okay, so let's talk about the advantage of this method. So first one is that you can determine the conversion of the reaction. Second, you can determine the yield of the reaction. And the third is that if you perform this reaction in deuterated solvent, then you don't need to do any evaporation, just directly take 0.5 ml and go for the NMR. So real-time monitoring can also be done through this method, and you also minimize the losses through the workup.
right? If you do workup procedure, then in that case you can lose some of the compound. But here is no workup, just directly you are taking and going for NMR, right? So this is the these are the advantages of this method. But what is the limitation is that internal standard need to survive throughout the reaction condition. If the reaction condition is harsh, it can decompose slightly, right? So it has to survive throughout the reaction condition. This is the problem. And second problem, if the reaction is complex reaction mixture, then you can see the overlapping of the signals. But still you can avoid this overlapping, because if you use this type of internal standards which I have told in this video, because they are giving two signals, so one can overlap, but another there is a possibility that you might see without overlapping, right? Okay, so that's all for today. If you want me to make video on method 2, so let me know in the comment box. I will cover in the next video. Till then, take care, bye bye, and don't forget to subscribe my channel.